Good. If you recall, in our first lecture we said data mining, data assimilation and prediction are parts of a continuum. Data mining relates to development of models. Almost all the models that have come to be originally arose from considerations that can be related in one way or the other to the concept of data mining as we understand it today. Once the notion of a model was well established, the notion of being able to use the model to create prediction came about. Once we are able to predict, the interest became improving the quality of prediction became fundamental, became a problem of fundamental importance. How do you improve the quality of prediction? You need to use the data. So data assimilation is a process by which you can fit the model to the data so that the model can be calibrated to make reasonably good prediction. So I have created the model, I have observed the data, I have created the assimilated model. What is next? To create prediction. So in this course we are going to see the various aspects of the quality of prediction. Who controls the quality? What is predictability? What are the why is the interest in predictability studies? And that's the theme of this last set of modules. So first we would like to be able to split our discussion of predictability into deterministic predictability, where deterministic refers to prediction generated by a deterministic model. Stochastic predictability relates to predictability of analysis of predictions arising from stochastic models. So as a starting point, we are going to talk about what is called error dynamics or variational equation, which we have already alluded to when we talked about 4D war methods. So we will quickly start developing some of the basic tools that we would need in the analysis of deterministic predictability. Let xk plus 1 is equal to m of xk alpha be a deterministic model. X naught is the initial condition, alpha are the parameters. Now let us consider the model running from one state called x naught bar, another state called x naught. So that is one prediction, there is another prediction. The trajectories is also called orbits. So let xk bar, let the sequence xk bar, the sequence xk be, so what is the sequence? x1 bar, x2 bar, xi bar, here is x1, x2, xi. So let us consider two orbits or two trajectories generated by the model starting from two different initial conditions. Let epsilon k is equal to xk minus xk bar. Therefore the initial difference is epsilon naught. The initial difference is epsilon naught. Then this difference is epsilon 1, this difference is epsilon I, this difference is epsilon k. So what is epsilon k? Epsilon k is the difference in the forecast of the model at time k induced by the difference epsilon naught in the difference in the initial condition that is used to generate the two different forecasts. So epsilon k is called the, so if epsilon naught is the error in the initial condition, epsilon k is the induced error in the state of the system at time k. Why is this important? In many of the 4D war based methods as well as forward sensitive methods within the context of deterministic dynamic data assimilation scheme, our goal has been to be able to estimate the initial condition. The estimate of the initial condition based on finite samples will always have errors. Therefore, if you used one set of observation, I will get one estimate for the initial condition. If you use another set of observations, I will use another set of initial conditions. So, no matter which method you use, if you are trying to estimate the initial condition from a finite set of observation, the estimate will not be equal to the true value that I would need to be able to make better forecast. In other words, estimates have always errors embedded in them. So you can think of epsilon naught as the error in the initial condition estimate. So if I want to give some life to this trajectory, let x naught bar be the true unknown initial state. So this could be the true trajectory. This could be the trajectory, this is the predicted trajectory. This could be the predicted trajectory. The predicted trajectory is different from the true trajectory because the initial state that is used to generate the prediction was different from the true state. The initial state estimate, so you can think of x naught as the estimate of the initial condition. The estimate epsilon naught is the error in the initial condition. So the error in the initial condition, however small it is going to be reflected in the forecast. I am interested in the error dynamics. So the evolution of epsilons induced by the model is called the error dynamics. That is the title of this slide. So I would like to be able to now derive an equation for the evolution of epsilon based on the evolution of the true state as well as the predicted state. So what is that one would expect? If the error in the initial condition is small, if the prediction at time k, the error is closer to the true state, that means the error in the prediction at time k is also small. In other words, small initial errors leads to small errors in the forecast at future time, then you would say the model forecast is more reliable. If the error in the initial state explodes in time, then the quality of prediction given by the model deteriorates in time. So what does this relate to? It relates to the sensitivity of the model to the variations or errors in the estimate of the initial condition. So if the initial errors are magnified by the model, that means the model is very sensitive. If the initial errors do not grow but goes down to 0, that means the models are more stable. So stable models can be used to create better prediction, but not all models are stable. So the quality of prediction depends on essentially to the sensitivity of the model to errors in initial condition. This is the fundamental theme of predictability analysis. This is the fundamental theme of predictability analysis. So that is the pathway we are going to be taking in this set of slides that describes analysis of deterministic predictability. So let xk plus 1 actual model using is the actual model starting from the state x naught. Now to a first order approximation, I can say the unknown true state is equal to the known prediction plus epsilon k. So it is again a first order theory. So xk is equal to this xk can be replaced by the true state plus epsilon k alpha. So here what is that I am assuming? Alpha is the parameter. You know, if I change the alpha, the solution changes. So I am going to pretend for a time being I know alpha precisely, and I have used alpha, the precise value of alpha. If there is going to be a forecast error, it is all due to only errors in the initial condition and not the errors in the parameters. So I want to separate I don't want to assume errors in too many things. Again, I want to emphasize the forecast errors can come from errors due to 3 sources. One, errors in the initial condition, errors in the parameter, or errors in the model. I want to be able to enjoy, analyze each one of them separately. So in this case, what is that we are interested in? Assume the model is perfect deterministic. Assume I know all the parameters in the model absolutely precisely. So if there is any forecast error, that is directly attributable to only errors in the initial condition. And the errors in the initial condition, where do they come from? They come from estimates. While data assimilation schemes gives you reasonably good estimates, optimal estimates in some sense, because the estimates are derived out of finite number of samples, the estimate from the finite set of samples may only be closer to the true value. Still, there could be a non-zero error. Our aim is to be able to see how the model treats this more often inevitable error, the error coming from estimation of the unknown initial condition based on finite samples. So that's the kick, that's the real key. So if I now express this map in the form of a Taylor series, it can be seen, this is the base value, this is the perturbation. So from here, if I so please also remember xk plus 1 bar is equal to m of xk bar plus alpha. Therefore this equation becomes this, because this is equal to xk plus 1 bar, xk plus 1 minus xk plus 1 bar is epsilon k. The right hand side is becoming the Jacobian of m at time k. At time k means what? At evaluated at xk times epsilon k. So this becomes the dynamics for the evolution of the error, where dk is essentially d of xk of m. I didn't want to complicate the notation, so d of xk of m is simply dk. So what does this tell you? Epsilon 1 is equal to d0 m epsilon 0. Epsilon 2 is equal to d1 m epsilon 1, which is equal to d1 m times d0 m times epsilon naught. What is this? This is the Jacobian evaluated at the first state. This is the evaluation at the next state. So it's the product of Jacobians. This equation 3 in mathematics is called the variational equation. In meteorology literature, it is also called the tangent linear system. So in the context of 4D war, we consider tangent linear system essentially with respect to understanding the propagation of perturbation. Here, there we thought of inducing a perturbation initially to be able to correct the forecast errors. Here there is no correction, there is no data, there is no we have already done the data assimilation. So I have a model, x naught be the estimated initial state. I am going to run the model from this estimate. I am going to compare the performance of an assimilated model with respect to the unknown true state, and that is the analysis we are trying to do. So this is the post data assimilation analysis of model forecast, to be able to see how the initial errors are treated by the model. So I am naturally interested in 3 refers to the dynamics of evolution of the model errors. So if I iterate 3, I get this expression. What is this expression? If I picked 2 instances in time, yeah, I'm sorry, this is 0, this is time s, and this is time k. I would like to be able to express how the error at time s is related to the error at time k, and that is the relation. So s could be 0 or anything else. So this is general expression. This tells you how the errors at 2 instances in times separated in time are related by the dynamics. D of k colon s of m is simply the product of the Jacobian evaluated along the trajectory from time s to time k. This matrix has a special name. It is called a propagator matrix. What does it do? It tries to relate the errors between two different instances in time. The propagator matrix is simply a product of the Jacobians. Now I am going to introduce a numerical measure. Please understand, the error epsilon k. So I have now understood how the errors propagate to a first order accuracy through the model. Now, but errors are vectors. We understand certain scalar measure better than vectors. So I am now going to introduce a scalar measure that tries to quantify the properties of errors, and that is done by a quantity called Rayleigh coefficient. The Rayleigh coefficient is simply the ratio of the square of the energy norm of the error at time k plus 1 to that at time 0. So in the previous slide we related the error at time k plus 1 to error at time s. Error at time k plus 1 epsilon k plus 1 is a vector. Error at time s is a vector. S in general could be 0 or any number less than greater than 0. So S is greater than 0, less than or equal to k. So that is essentially the range for S. So epsilon k plus 1 is given by the product of Jacobian from k to s of m times epsilon s. Energy norm, I am trying to evaluate a numerator with energy norm based on an SPD A, the bottom line SPD B. So A and B, let A and B be two given symmetric positive differential matrices. Evaluate the numerator using the energy norm based on the matrix A. Evaluate the denominator using the energy norm based on the matrix B. In principle A and B could be equal, but the treatment is as simple when you do not have to consider A and B. For example, what could be the thing? In meteorology, I would like to be able to say, hey, initially I am interested in pressure, but at a later time I may be interested in certain vorticity. Initially I may be interested in temperature difference, at a later time I may be interested in rain. So what do A and B bring to the bring to bear on the problem? I would like to be able to consider the sensitivity of the rain at a future time, and it depends on a temperature distribution to the previous time. I may be interested in some quantity at a later time and its sensitivity based on another quantity. Therefore, at this stage when I am trying to talk about quantities, sensitivities, I do not have to make them to be the same. Therefore, Rayleigh coefficient, what is it? It is simply the ratio of quadratic forms. What is the quadratic form? So the numerator, so Rk plus 1 epsilon is essentially equal to epsilon k plus 1 transpose A epsilon k plus 1 divided by epsilon s transpose B epsilon s. That is exactly the relation that's involved in here. Now please understand, epsilon k plus 1 and epsilon s are related through the model. The relation through the model is given by the product of the Jacobian along the lines. So how does the initial so what is that you can think of it now. Suppose I have a grid, I have an initial condition, I have a model. I'm going to introduce a thermal bubble in a small locale at the initial time involving certain small number of grid points. So that is a perturbation of temperature distribution initially. How does the model reacts to the thermal bubble at a time in the future? How does this thermal bubble introduces other changes in the model? So that could be one way of thinking about this ratio. So A and B in general are two symmetric positive differential matrices. This ratio is called the celebrated Rayleigh coefficient in matrix theory, and that comes to our that's a very useful measure for us to be able to consider predictability analysis. So I would like to be able to understand the behavior of this ratio. Now let us see what this ratio represents. This ratio in general represents a measure of the sensitivity. You can see the energy in some quantity at a later time related to the energy of some other quantity at the initial time. So this ratio captures the spirit of the sensitivity that is involved in the predictability analysis. Suppose this ratio remains less than 1. Okay, this ratio is a scalar, right? If this ratio remains small for all time beyond s, what does it mean? The error does not grow. If the error does not grow, what does it mean? The predictions are pretty darn accurate. On the other hand, if this ratio grows in time, what does it mean? The errors, the initial errors magnify. Therefore, analysis of the properties of this Rayleigh coefficient for appropriate choices of energy norms of the numerator and the denominator essentially provides a very good clue to the quality of forecast generated by the model. That's the secret of using Rayleigh coefficient. So in order to further analyze the Rayleigh coefficient, let us concentrate on the propagator matrix. What is the propagator matrix? It is a product of the Jacobian from time s to time k. Let us call that matrix A for the sake of simplicity in notation. I am also going to assume the model Jacobian is non-singular. If the model Jacobian non-singular means what? The model is well formed. Non-singularity of the Jacobian at every point along the trajectory goes to attest to the well formed nature of the model itself. The model, sometimes the model could be screwed up. How do you measure? What is the measure of the screw up of the model? Look at the Jacobian. The model actually gives you a solution. You try to evaluate the value of the Jacobian along the trajectory. If the value of the Jacobian remains full rank, the model is well formed. If the rank of the Jacobian along the model varies, then the model is not well formed model. So I am assuming the model is well formed in the sense that Jacobian along the trajectory are non-singular. Okay, now A is a square matrix. Please realize that A is a square matrix. Even though A is a square matrix, in general A is not symmetric. A depends on the starting time s and the starting time k. So if I vary any one of the timings, A changes. But for the analysis, I am keeping s fixed, k fixed, so A is fixed. So A transpose A and AA transpose are the two Gramians coming out of this model. Both of them are SPD. Why both of them are SPD? If each of the components of a component matrices in this product are non-singular, the product is non-singular. If a matrix is non-singular, its Gramian is full rank. The Gramian is not only full rank, is also symmetric and positive definite. These are all immediate conclusions we have alluded to several times earlier, especially within the context of development of SVD, singular value decomposition. So let V1 to Vn be the eigenvalues. This is the eigenvectors of the matrix A transpose A. So A transpose AV is equal to V lambda, VV transpose V transpose V is I. Now I am going to define a new vector Ui, which is equal to 1 over lambda. I am using the similar formalism as we did in the SVD. The only difference is earlier we defined SVD for the context in the context of matrix H, which is rectangular. Now I am talking SVD within the context of the matrix A, which is square. H is a single matrix with a forward operator. A is a complex matrix, is a product of matrices along the trajectory. If I assume each of the matrices, each of the Jacobian matrices are non-singular, A is non-singular. So I am just trying to reinforce the idea where A comes from. So if Vi's and lambda i's are the eigenvector eigenvalue pair for A, I can now define a new vector Ui. Ui also is an n vector, which is 1 over square root of lambda I times AVI. From this derivation, so I am now going to compute AA transpose Ui If you substitute the expression for ui and simplify it, it turns out I get 9. So what does 9 say? A transpose ui is equal to lambda I of ui. So what does it mean? If vi's are the eigenvectors of A transpose A, ui's are the eigenvectors of A transpose. Both the matrices share the same set of eigenvalues. In this context, the lambda i's are the eigenvalues of A transpose A as well as A transpose. Both of them are matrices of the same size. So square root of lambda I is called the singular value. That is the definition. So singular value of a matrix is the square root of the eigenvalue of the Gramian. That is the definition. And the square root of the eigenvalues of the Gramian are all going to be positive if the Gramian is symmetric positive definite. A Gramian is symmetric positive definite if the component matrices are a full rank. So full rank condition essentially tells you the problems are well formed, and that is a condition we have been looking at all through. Full rank matrices, all good things in life, and that is exactly the kind of theory we have developed. So square root of lambda I are called the singular values. VI's are called the right or forward singular vectors. UI's are called left or backward singular vectors. These are the general nomenclature that is well understood within the applied mathematics linear algebraic context. Now from 8, I am going backward. I would like to talk about some of the properties of equilibria. From 8 I can rewrite my equation for the definition of ui this way. There are n such a, if I collected all the relations the matrix form, it becomes a matrix version. So 11 is the matrix version of 10. Therefore A transpose A is given by this decomposition, because u transpose u, they are all identity. U is orthogonal, V is orthogonal. Therefore I get this expression. So the columns of V are orthonormal system. So what is that we are now going to do? We have been doing the analysis in the general coordinate system given by the standard basis, which is EI. What is the standard basis? EI is equal to 0 1 0, and this is the ith location. I for 1 to n, that is the standard basis. If I have any other basis, I can do the analysis in that basis. Why would you change the basis? If the analysis in the new basis can be made simple, nothing is lost. In fact, a lot may be gained by changing the coordinate system from the standard to a given coordinate system. So now we are going to gain by changing the analysis from the given simple coordinate system to an orthogonal system defined by V, the columns of V. What are the columns of V? They are the eigenvectors of the matrix A transpose A. Given a space, we should always have n basis vectors. If the basis vectors are orthogonal, it becomes orthogonal basis. If the basis vectors are not orthogonal, it is a basis, but doing arithmetic in non-orthogonal basis is a little bit more involved. So we are simply changing from one orthogonal basis to another orthogonal basis, and that is going to throw a lot of light on the behavior of the Rayleigh coefficient. So what is the transformation we are going to be talking about now? Please understand, epsilon s is the initial error at time s. V is the new basis. So I am going to transfer epsilon s to alpha. So what is alpha? Alpha is the new vector. Alpha and epsilon n are referred to the same point in this space. Epsilon s is the coordinate of the same point in the original basis. Alpha is the coordinate of the point in the new basis whose columns whose basis vectors are columns of V, and these two values of coordinates of the same point in the two coordinate system are related by the expression in 13. Therefore now I am going to re-express my value of the Rayleigh coefficient at time k plus 1 with respect to the Rayleigh coefficient at time s. This is the definition of the Rayleigh coefficient in the standard basis, which is 14. In the transformed domain, my Rayleigh coefficient takes this form. So what is that I am going to do? Please remember, my A is equal to D colon S of M. So A transpose is equal to D Ks S transpose of M. Also remember, my epsilon S is equal to V transpose alpha. So if you substitute all this, 14 becomes 15. 14 becomes 15. What is the real kicker here? The real kicker, the numerator and the denominator get simplified. What is that? A transpose AV is equal to lambda V, because V, the columns of V are the what eigenvectors of that. Therefore, if I multiply this by V transpose A transpose AV, that is equal to lambda, and that is exactly what is occurring in the numerator. Therefore, this complex matrix in the numerator becomes simplified as a diagonal matrix in the numerator. We also know V transpose V is equal to V transpose, that again comes from the orthogonality eigenvector, that is equal to I. The denominator gets simplified by this. Therefore, I have decoupled both the numerator and the denominator from the dependence. And so in here, what are the various values of A? I am assuming A is identity. I'm sorry. I'm considering the energy norm. I don't think I want to go back right now. Sorry. So I hope this is clear now. The expression for the Rayleigh coefficient is given by 15. Now what is the so denominator 15? What is that? Is the inner product of alpha with itself. The numerator is simply a quadratic form of alpha with respect to diagonal matrices. So what is the so now what is that? So alpha is a vector. So alpha is any vector that is going to represent my epsilon S. So I am going to now consider a normalized vector. So the norm of alpha defined by this, I am going to set to be 1. What does this mean? If I have a vector here, I can consider the normalized part of it. So that is essentially a normalization. The direction is more important than the magnitude itself. That is the idea here. So I am going to consider the ratio in 15 when I confine my attention to alpha unit vectors. That's the whole point of the game. So in this case, the numerator becomes 1. Therefore, RK plus 1 alpha is essentially the numerator, which is alpha transpose lambda alpha, which is again given by lambda I square root square of alpha I square. From here, the following inequality becomes follows directly. This is the value, the actual value. Since the sums of alpha I square is 1, so you can readily see lambda I alpha I square I is equal to 1 to n is less than or equal to maximum over I of lambda I times alpha I square. I is equal to 1 to n, and that is equal to 1. So that gives rise to this. This is also right minimum over I of lambda I square times summation alpha I square I is equal to 1 to n, that is equal to 1. Therefore, lambda 1 is the maximum eigenvalue, lambda n is the minimum eigenvalue. It readily follows RK plus 1 alpha is less than or equal to lambda 1 and lambda n, where lambda 1 and lambda n are the maximum and minimum value of the eigenvalue. So what is it we have done? We have narrowed the values that the ratio of the energy norms of the errors can take by moving simply from the standard coordinate to the new coordinate formed by the eigenvectors of the Gramian A transpose A, assuming A is full rank. So this is a very nice treatment of the analysis of the Rayleigh coefficient. Now what is that we are interested in? We are interested in determining what is called the average rate of growth of errors from time s to k plus 1 when k goes to infinity. That is of interest. Let us look at this. Why are we interested in the average growth of errors? If I commit an initial error, if the error grows, how much error I can afford to corrupt my forecast such that forecast is still meaningful is the question. For example, in weather forecasting we have made tremendous improvement over the past 50 years, but we still do not know how to make monthly forecasts. Our models are some of the best known models in the last 100 years. We have the best computers, we have all kinds of observation systems. We still cannot make predictions over so the predictions that we make in today with all the things we know, with all the technologies available, computers, sensors, satellite models and everything else, we can probably believe 3 to maximum 4 day forecast. So what is 4 day? 4 day is the predictability limit. So what does it mean? Today I am going to make 1 day forecast, 2 day forecast, 3 day forecast, 5 day forecast. The error in 1 day forecast is there but smaller. The error in the 2 day forecast is slightly larger. The error in the 5 day forecast is more. Why do you don't want to do the 10 day forecast? It is not that I don't know how to make a 10 day forecast. I can make the 10 day forecast too. But the error by the time 10 days into the future comes into being is so much that it dwarfs the signal. So there is a signal on which the forecast error is superimposed. If the magnitude of the superimposing error is comparable to the signal, then signal plus noise overwhelms the information. So it's a classical study in the engineering literature called signal to noise ratio. So in any estimation problem, in any detection problem, we will always like to be able to analyze the signal to noise ratio, and we would like to be able to maximize the signal to noise ratio. So in some sense the Rayleigh coefficient tries to capture the spirit of the computation of signal to noise ratio. So one question is to how far does it take to be able to double the initial error? So what is the norm of the initial error? What is the norm of the error at a future time? How long does it take for the initial error, the norm of the initial error to double? That is called error doubling time. If the error doubles in 10 days, after 10 days the error is even more than double. So can I make a forecast where the error is double than the initial one? No. So what is the amount of error you may be able to tolerate? How far the error grows, how fast the error grows. Okay, the error rate of growth varies from time to time to time to time. So if the error rate of growth varies from time to time to time, what is one measure? Average rate of growth of errors. So to understand the quality of prediction, we need to understand the predictability limit. What is the predictability limit? Predictability limit is the limit beyond which errors overwhelm the signal. If the errors overwhelm the signal, the prediction is useless. Now here comes some of the basic things. Some processes are predictable perfectly. The lunar solar eclipse. IBM price I can predict for tomorrow, but I don't think I can predict the price of an IBM stock day after tomorrow. It's much more volatile. There are lots of factors that depend on. How do you predict the price of a barrel of crude oil? The barrel of crude oil depends not only on the cost of production but also the cost of transportation from place A to place B. Either you transport the unpurified base liquid or purified form, but then the cost of crude oil is controlled by so many events in the world. If there is a war in the Middle East or if there is a problem in the Middle East, we believe that the supply may be affected, the price immediately goes up. So there are a number of factors that affect the price of a barrel of crude. So the barrel of crude, predictability of it is extremely difficult problem. So likewise the weather prediction, we have gained enough knowledge about the weather, the behavior of it, so that we can make good short term prediction. Long term prediction we try to do, but we are not able to do long term prediction which are reliable. For example, I cannot predict seasonal weather precisely. I don't, let alone climate. Why? It is not because we are not intelligent, because the model we use exhibit extreme sensitivity to the initial condition. So the initial condition you use to generate the forecast have even smaller errors. If the model is very sensitive to small errors, the errors blow up in time. So that is the fundamental theme behind predictability analysis. So the interest now goes to analyzing what is the average rate of growth of errors. That is important. So what is, so given yes as a starting point fixed, this is k, I would like to go to infinity. So from a fixed starting point, if I want to be able to make asymptotically large values of time, and if I want to be able to make forecasts for such large values of time, over that time what is the average rate of growth of errors as seen through the model. To that end, I am going to define a new matrix. So what is this matrix? You remember DKSM, which we have also called A. I am going between A and this whenever we need to. So this is simply A transpose A, that is the Gramian. S is fixed, S is fixed, it depends on M. I am going to let k go to infinity. So I am interested in the long term value of the Gramian A transpose A. I am also interested in the 2k minus 1, 2 times k minus 1, the root of this matrix. Please understand, given a matrix A, I can consider A square. Given matrix A, I can consider A to the power of 1/2. Given a matrix A, I can consider A to 1 over alpha for some alpha. So this is the matrix. I'm considering 1 over 2 times k minus s. What is k minus s? K minus s is the time difference between the starting point and the final time. K goes to infinity. So k minus s goes to infinity. So this matrix plays a fundamental role. The eigenvalues of this limiting matrix are called Lyapunov vectors, and the corresponding eigenvalues of this limiting matrix are called Lyapunov numbers. We are going to talk about these too, but before we go there, I would like you to be able to appreciate the definition of this matrix. So what is this? It is a product of the it is the product of A transpose A. A transpose A is the Gramian. A transpose A depends on S and K. I am keeping S and M, the model, fixed. I am letting K goes to infinity. I am interested in the 2 times K minus S, the root of this product matrix, and that is the matrix, that limit matrix. That limit matrix has an eigenvalue, eigenvectors. The eigenvalues are called Lyapunov vectors, eigenvalues are called Lyapunov numbers. Lyapunov is the famous Russian mathematician who propounded the theory of stability in the early decades of 20th century, and so in his honor it is called Lyapunov vectors, Lyapunov numbers. The natural logarithm of the Lyapunov numbers are called Lyapunov indices. So let us look at this number. So this is called Lyapunov indices. Lyapunov index. So what is the Lyapunov index? It is the Let's look at this now. Let us look at this ratio. What is this ratio? It is the norm of the error at time. So if I have time s, if I have time k, I have epsilon s, I have epsilon k plus 1. The norm of the ratio of the, so this is equal to d k times s of m of epsilon s. So the norm of the error epsilon k plus 1 divided by epsilon s. So what does it tell you? By running epsilon s through the model, I am able to change the initial error. So the norm of this ratio is a number, and this number depends on the time interval k minus s. I am going to normalize this by 1 over k minus s. S is fixed, k goes to infinity. So this ratio is the, you can think of it as the average. So this average value lambda is called the Lyapunov index, and this Lyapunov index essentially tells you the average rate of growth of errors. That makes sense. I want to think about it now. So epsilon k plus 1 by epsilon s, what does it mean? That is the rate of growth of error during the time from s to k. I am trying to divide it by 1 over k minus s. So that is the average rate of growth of errors. So what is the meaning of this Lyapunov index? I am going to introduce it by illustrating it on a scalar dynamics. In fact, the entire theory of dynamical chaos in deterministic system is centered around this notion of Lyapunov indices, average rate of growth of errors, sensitivity to initial conditions. So what is the idea? If a system exhibits extreme sensitivity to initial condition, that system cannot be used to generate prediction for long intervals of time. If the system exhibits less sensitivity to initial conditions, such systems can be used to create long term forecast. It turns out most of the models of interest in climate studies, most of the models of interest in oceanography, atmospheric sciences do exhibit extreme sensitivity to initial condition. That is the reason why we still are not being able to make 10-day forecast, a monthly forecast, seasonal forecast. We still have not captured all aspects of the model sensitivity. So the current models exhibit extreme sensitivity. That is the reason why we are able to do what we are able to do. So to understand this, let us work a simple example. Let x dot is equal to f of x be a dynamical system. If x naught bar is the given initial condition, that is the unknown, that is the true value of the state. So this is x naught bar. So from here I can compute the solution x of t. I have x naught, this is x naught bar, I can compute x of t. So barred quantities are true, unbarred quantities are coming from estimated values. I have an initial difference which is epsilon naught. I am doing the entire theory, but based on a simple one dimensional models. So the dynamics of the error growth, the variational equation for this case becomes y dot t is equal to Jacobian of f times y of t. This y plays the role. So instead of epsilon, I am going to consider this as y naught. So let y naught be the initial difference, let y of t be the difference at time t. Epsilon we use in the context of discrete time, y of t I am going to use it in the case of continuous time. So y of t is related to the rate of growth of y of t is given by this equation. This equation is a linear dynamical system. The linear dynamics varies along the trajectory again. So this is the Jacobian. If you discretize this in the interval 0 to t, there are n subintervals. Let the subintervals of time tau, so n tau be t. So this is 0, this is t. I am going to divide it into intervals where the subintervals are time are of length tau, and t is equal to n tau. So now I am now going to assume that this equation, which is given by 21, is such that during a given interval of time my dt of f remains constant. That means the interval of time tau is so small that my Jacobian does not change too much within that small interval of time. Therefore, I am now going to assume the dt of f in a small interval going from k tau to k plus 1 tau, it remains constant, and that constant value is Lk. So what is Lk? Lk is the constant value of the Jacobian of the system during the time of evolution from k to k plus 1 or k tau to k plus 1 tau. If tau is small, this is a reasonably very good assumption to make. Therefore y dot dt of f yt by combining 22, so 22 when substituted in 21 becomes an equation like this, becomes an equation of this type. That is a linear equation. This equation depends on k, you can see Lk depends on this interval. I can solve this equation very readily, that is yk plus 1 is equal to e to the power of Lk tau yk. So if at time k, this is time k plus 1, if yk is the initial condition, I would like to be able to compute the solution at yk plus 1, the matrix Lk remains the same. So the solutions at two intervals of at two endpoints are related by this equation 24. If I iterate this from y0 to yn, I get this relation. You can readily see by iterating 24 and using the definition of Lk being constant in that domain. Yn is equal to e to the power of summation j is equal to 0 to n minus 1 Lj times tau y0. Now from the definition of the Lyapunov index, the Lyapunov index at time t, I am assuming my forecast horizon is capital T. So when my forecast horizon is capital T, from the definition of 20, no, it should be tau going to 0. So this should be, sorry, as tau goes to 0, not t. So t is fixed, tau goes to 0, as tau goes to 0 n goes to infinity, n tau represent the total time capital T. So n tau is always capital T, please understand, n tau is capital T. So as tau goes to 0, n goes to infinity, but the product is fixed T. The product is fixed T. Now I am taking the logarithm of yn divided by y0. What is yn? Absolute value of yn is the error at time capital N. Y0 is the error at time 0. I am taking the ratio. It is the logarithm of the ratio of the magnitude of the error at time n to time 0. So why are the errors now? I am interested in the errors that affect the prediction. Now if I substitute 25 the expression for yn in here and simplify, what does it become? It essentially becomes the average of Lj, that is L bar T. Hey, that is a beautiful expression that comes from a simple. So lambda T, which is the function of T is finite, it becomes L bar T. What is L bar T? It is the average value of the Jacobian along the trajectory. That is beautiful, that is just beautiful. So lambda T refers to the mean growth of errors during the interval 0 to T. Now what do I want to get the Lyapunov index? Let T go to infinity. That is the definition of Lyapunov index. So what is the Lyapunov index? Is the limit of capital is the limit of lambda T with a capital T going to infinity, and that gives rise to the definition of average rate of growth of errors in unbounded intervals. So what does that tell you? If lambda is defined that way, you can now see that yt at any time is equal to e to the power of lambda t times y0. Clearly the error grows when lambda is greater than 0. So what does it mean? One can analyze the quality of prediction by analyzing lambda. If lambda is greater than 0, what does it mean? Average rate of growth is greater than 0. If the average rate of growth is greater than 0, error grows. So in systems where lambda is greater than 0, there is an inherent predictability limit. In systems where lambda is less than 0, there is no predictability limit. I can predict for the whole future. So that is the import of this analysis. So I want you to go back and understand the theory reasonably well. So we presented a general theory. We are trying to illustrate the general theory based on a very simple scalar continuous time dynamics. We have introduced the notion of average growth of errors. So it is the average rate of growth of errors over asymptotically long intervals of time that helps to indicate the quality of prediction generated by the model. So lambda depends on the model. So lambda is going to be able to give us the guideline how to believe and how long I can believe the forecast generated by the model. So how do we define the predictability limit? The predictability limit Tp is given by Tp is equal to 1 over lambda. So if lambda is positive, my prediction can hold water only up to the forecast horizon Tp, which is equal to 1 over lambda. So what is 1 over lambda? If y of t is equal to e to the power of lambda t y naught, if t is equal to Tp y naught, if Tp is equal to 1 over lambda, y of t is equal to e times lambda y naught. That means the ratio of the magnitude of the initial ratio of the magnitude of the error at time t to the initial error is of the order of e. Hey, that's the predictable limit. This limit for atmospheric models used to be 1 or 2 days about 3-4 decades ago. Now has gone to of the order of 5 to 7 days. It is this improvement from 1 to 2 days to 5 to 7 days is the achievement by the meteorological community by bringing in the science of data assimilation and analysis of predictions created with the model. So you can see the role of data assimilation, the role of errors in the initial condition, the role of trying to measure the ratio of the errors at 2 different times and understanding the rate at which the errors grow. These are some of the beautiful mechanisms using which one can create estimations of how good a forecast is. That's the ultimate key. So creating forecasts is one thing, trying to attest the goodness of the forecast is something else. We have learned how to create forecasts by so many different methods of data assimilation. The analysis of data assimilation is not complete until we understand the predictability limit, how long the prediction can hold water. That is the idea here. So that is for time greater than Tp, Tp is the predictability, for time greater than Tp, the error in the initial condition will overwhelm the signal corresponding to the base forecast. Clearly lambda is a function of x naught, so and the given value of the parameter. Lambda varies as the function of the initial condition, also the parameters. Now I am going to talk about how to compute lambda for real systems. So we have seen the importance of Lyapunov index. Now I am going to talk about a renormalization strategy by which one can implement an algorithm on any model to be able to compute the Lyapunov index. Once a quantity is of great interest, we need to be able to compute it. So let us look at an algorithm now. Let epsilon naught be the initial value of a perturbation based on the initial condition x naught bar. So initial condition is fixed, given model is fixed, alpha is fixed. So please understand, my model is xk plus 1 is equal to m of xk alpha. So m is fixed, alpha is fixed, I have initial condition that is also fixed. So if I am interested in the ratio epsilon s to epsilon naught, epsilon s to epsilon naught, I can essentially express this a product like this. So what is that? Epsilon s divided by epsilon s minus 1 times epsilon s minus 1 divided by epsilon s minus 2, likewise epsilon 1 divided by epsilon naught. All the cross terms will leaving behind, this is equal to epsilon s divided by epsilon naught. Therefore, this ratio is equal to the product of the ratios between two successive times. So, what is that we are interested in? We are interested in 0 s. I am interested in trying to multiply the product. I am sorry, I am interested in the ratios two successive times. The product thereof gives you the product from epsilon s to epsilon 0. So, you can readily see this product is given by this ratio. So, then from our definition, what is lambda, the Lyapunov index? The Lyapunov index is the average of the log of the so I have to take the log of both sides. If the log of both sides, log of the product is the sum of the logs. So, logarithm of AB is equal to log of A plus log of B. So, if I took the logarithm on both sides of 30, I get an expression. So, the ratio of the log of both sides as epsilon naught goes to 0. So, I would like my epsilon naught to be as small as possible. I want my n to go to infinity. What is n? The number of discrete intervals of time, and that is the limit of the average of the logarithm of the amplification along the trajectory. That's the basic idea. So, I would like to be able to compute this. If I can compute 31 using a clever algorithm, I am done. And to be able to express 31, the key is in expressing the ratio of the errors, ratio of the norms of errors at time s to time 0 as the product of ratios at consecutive times. So, this is the product of ratios at the consecutive times. The product of the ratios consecutive times, the numerator denominator cancels, leaving behind epsilon s and epsilon naught. So, that is a very clever way of writing the ratio of the norms at time s to time 0. So, this is one of the ways of computing there. So, how do we do that? So, here is an algorithm now. So, let epsilon naught, I'm sorry, that's right. Let epsilon naught be the initial error. Then run the model one step interval at time, compute the error epsilon 1, compute the ratio, the norm of epsilon 1 by norm of epsilon 0. Then run the model from epsilon 1 to epsilon 2. Then multiply this by norm of epsilon 2 times epsilon 1. Continue. If I continued, I get epsilon s divided by epsilon s minus 1, that is equal to norm of epsilon s divided by norm of epsilon 0. So, by running the model one step at a time, by computing the ratios, by taking the product of those ratios, taking the logarithm of the ratio, I can in a way estimate lambda. So, this provides an easy algorithm to be able to evaluate lambda. So, this is what is called renormalization strategy. Now, I am going to give you well known information about certain facts about Lyapunov indices. For forced, okay, I have not defined what a chaotic system. Now, let me talk about the definition of a chaotic system. When do I say a dynamic system is chaotic? If given a dynamical system, if you compute the Lyapunov index, if the Lyapunov index is positive in some part of the domain, then it is called chaotic. Why it is chaotic? In a chaotic system, error grows on an average rate. If the error grows on an average rate, then the predictability becomes very difficult. So, what is the measure of that predictability is Lyapunov index. So, Lyapunov index is being positive is one of the signatures of the chaotic system. And also lambda greater than 0 is an indication of the fact that the system is extremely sensitive to initial condition, because initial condition errors grow at a rate lambda. So, Lyapunov index sensitive to the initial condition, being chaotic, all these things are related concepts. So, given a forced chaotic system, the first Lyapunov index is positive, which is responsible for the sensitivity to the initial responsible for the sensitivity to the initial condition. Now, I only talked about Lyapunov index, you may ask what is the first Lyapunov index. Again, that requires a little bit of an explanation. You remember we talked about the matrix. Let's go back. In the definition of Lyapunov indices, we talked about this matrix in 19. Lambda m is a matrix. A matrix has m different eigenvalues. So I'm now, if I talk about the analysis of the first eigenvalue, that leads to first Lyapunov index, second eigenvalue leads to second Lyapunov index. So if a system, if the order of the system is 3, in general it should have 3 Lyapunov indices. I only talked about the maximum value of the Lyapunov index, or the Lyapunov index corresponding to the first eigenvalue. So an n dimensional system has n eigenvalues, n dimensional systems can have n Lyapunov indices. So if there are n Lyapunov indices, we can talk about the first, second, third and so on. I am now going to talk about some of the well known facts about Lyapunov indices for different types of systems. So for a dissipative system, the sum of all the Lyapunov index must be negative. That is a fact. This can be proven. It is proven on many good books on introduction to chaos theory. For this class of system, one of the intermediary Lyapunov indices is also 0. I am going to illustrate it further. These are some of the well known facts I am trying to summarize. Explaining each of this will take at least 1 or 2 lectures, but here I am trying to collect many of the results. The growth rate of the, so what is the lambda 1 tells you. So if I have a 3-dimensional system, I have 3 Lyapunov indices. Lambda 1 tells you the growth rate of errors along one line. Lambda 1 plus lambda 2 refers to the growth rate of surface areas. Lambda 1 plus lambda 2 plus lambda 3 refers to growth rate of specific volumes. That is where different Lyapunov indices come into play. So likewise, the sum of the first k Lyapunov indices tells you the rate of growth of k dimensional volumes. So these are all very many simple facts. So now I am going to talk about some of the specific values for specific systems. Many of us are introduced to the notion of Lorentz 1963 model. It was Lorentz in 1963 for the first time introduced or accidentally found the presence of chaotic system. So for it is this 1963 model of Lorentz is one of the most thoroughly analyzed and understood systems of differential equation. It consists of 3 ordinary differential equation coupled with nonlinearity. It is also a dissipative system. Because it is dissipative, it is in general does not go to infinity. The orbits remains bounded. The first Lyapunov index for this is 0.09. Therefore, e to the power of 0.9 is equal to 2.4596. So what does it mean? Any line segment, any error along the line, or any error along the line will magnify at the rate 2.4596. That is the average rate of growth of errors. But the total Lyapunov indices for this is minus 11.9. That means the 3-dimensional volumes decrease at this rate. So what is the idea here? The volumes decrease. The attractor where the orbits of the system exist, you cannot predict where the orbits will be at what time, because it is intrinsically chaotic, because lambda 1 is positive. So that is the overall characteristics of what is called the Lorentz system, and examples of values of the first Lyapunov index. If the first or Lyapunov indices are positive, then lambda prime p is equal to sum of all the Lyapunov indices which are positive, two states that are infinitesimally close diverge at the rate lambda bar e to the power of lambda bar p times t. So this is again the average rate of growth. This is an extension of yt being equal to e to the power of lambda t times y of t. So in this case it is yt times e to the power of lambda p times t times y naught, where lambda p is lambda bar p, where the lambda bar p is equal to the sum of the first r Lyapunov indices which are positive. So the sum of the positive Lyapunov indices refers to the average rate of growth. In this case the predictability limit is given by 1 over lambda bar p. Now you can see if there are more than one Lyapunov index that is positive, lambda bar p is larger. If lambda bar p is larger, 1 over lambda p bar is smaller. Therefore if a system exhibits larger number of positive Lyapunov indices, in such system the predictability limit is much smaller. If a system does not have any positive Lyapunov index, then I can make predictions for a long periods of time. So that is the ultimate essence of the theory of Lyapunov index. Now I am going to give you, these are exercise problems, but I am going to quote you some of the values of the Lyapunov indices of some of the very well known mathematical models. For the logistic model with the parameterization for the Lyapunov index is 0.6931, that is positive. So logistic models are chaotic because they are extremely sensitive to initial condition. There is a model called Henon model. The Henon model has the first Lyapunov index is a 2-dimensional. For the Henon model I have the lambda 1 is 0.42, lambda 2 is minus 0.162. For the Lorenz's model already talked about, first one is 0.9, second one is 0, last one is this. So these are some of the examples of simple systems. There is a difference between the properties of the logistic model is a discrete time model that tries to capture some of the principles of population dynamics. Henon model is a mathematically oriented model. It may not correspond to any particular physical system. Lorenz's model, how did he obtain the 3 differential equation? He obtained it from starting with some vorticity equation. In this case not vorticity equation, I am sorry. It is the heat transfer problem. And from that he applied the spectral methods, and he from that derived the 3 sets of equation whose eigenvalue whose Lyapunov indices are positive, 0 and negative. So Lorenz's model theoretically was the first one to be able to exhibit the notion of Lyapunov index and the role of Lyapunov index in predictability studies. Here are some other properties of Lyapunov indices. I am going to now create a comparison, steady state behavior, attractor, Lyapunov index, dimension of the attractor. These are summaries of a very well known result. A steady state for a dynamic system can be an equilibrium point. What is an equilibrium point? There is an attractor to which all the solutions come and settle down. Those steady state are called equilibrium point. Equilibrium point, the attractor is a point. The Lyapunov indices are all negative. Therefore the dimension of the attractor is 0. For a periodic orbit it is a cycle. There is one Lyapunov index is 0, rest of them are negative. The dimension of the attractor is 1. I know I have not talked about the dimension attractor much more elaborately, but I believe I wanted to provide you a quick summary of the notion of predictability and some of the models for which the predictability can be answered. So what does it mean? If a system exhibits an equilibrium, predictability is complete. If a system exhibits periodic orbit, the predictability is complete. I do not have to worry about predictability. I can predict for all time. If the system exhibits a steady state with respect to 2 periodic orbits, the attractor is said to form a torus, in which case 2 eigenvalues are 0 the rest of the eigenvalues are negative. The dimension of the attractor is 2. For a chaotic system, the attractor is called fractal. I have not introduced even the notion of a fractal object. Fractal object is a complicated object. In the case of a fractal object, in the case of a chaotic attractor such as the Lorenz's attractor, the at least one Lyapunov index is positive. The rest of them could be 0 or negative, and the sum of all the overall Lyapunov indices totally together could be less than 0. That indicates the system is totally dissipative, and the dimension of the attractor is non-integer. That means they have what's called fractal dimension. So the notion of fractal attractor, fractal dimension, chaotic behavior, they are all interrelated with each other. With that, we conclude our discussion of deterministic predictability. I would like you to pursue these this exercise. What is the exercise? Consider the simple logistic model. This is a very good exercise. Consider alpha. Consider this is not alpha A, the same parameter A as in here. Consider the range of parameters from 1 to 4. X naught is equal to 0 to 1. So I would like you to pick an X naught, pick an alpha, compute lambda. So plot. This is a very good computing exercise. Lyapunov index versus X naught for a given value of alpha. Sorry, for a given value of alpha. So alpha is equal to 1, draw this curve. Alpha is equal to 2, draw this curve. Alpha is equal to 3, 4, draw this curve. You will see. You will verify when alpha is 1 and 2 and 3, the system does not exhibit any sensitivity to initial condition, but when alpha is equal to 4, the system tends to exhibit extreme sensitivity to initial condition, and that is the model we talked about. With this, I conclude our discussion on predictability of deterministic system. As a quick summary, predictability analysis is of great interest after we assimilated data into the model. Once you assimilate data into the model, I have the capability to make prediction. The question is, how far, for how long the prediction will hold water. The answer to the question of how long the prediction will hold water depends on the intrinsic property of the model itself. It relates to the sensitivity of the model solution with respect to the initial condition. This sensitivity is essentially related to the forward sensitivity we have already defined. So forward sensitivity analysis and analysis of Lyapunov index are intimately associated with each other, even though I am not exploring that discussion in this set of lectures. One way to be able to summarize the initial condition sensitivity is through a parameter called Lyapunov index. Lyapunov index could be positive, 0 or negative. For dissipative system, the sum of all the Lyapunov indexes must be less than 0. At least one Lyapunov index is 0. If one of the Lyapunov indices, the greatest Lyapunov index is positive, such systems are supposed to exhibit extreme sensitivity. It turns out many of the models that are currently being used in geophysical sciences to predict different types of geophysical phenomena have exhibited extreme sensitivity to initial condition. That is the reason why we are not able to make long-term predictions despite 50 plus years of progress in model building as well as data collection and data analysis, and with all the advances we are able to increase the predictability limit to about 5, 6, no more than 7 days these days. So what does it mean? The prediction problem continues, it continues to dominate, it continues to be a problem of great challenge. And one of the goals of this study, models, data assimilation, all relates to improving the predictability limit. So what is the ultimate goal of doing all these things? I would like to be able to make long range prediction, very reliable long range prediction. Until such time we achieve the ability to make long range prediction, our job is not done, and there is no telling how long it may take. So it all depends on very many different aspects of models, data assimilation, sensitivity to the models to initial conditions, so on and so forth. So I have provided simply rudimentary ideas. I simply scratched the surface on predictability. It's a very deep discipline. I would encourage you, hope this will encourage you to be able to look at some of the interesting books related to predictability analysis as well as chaos theory. But as a starting point, this exercise, analyzing logistic model by choosing various alphas and choosing various x naughts and trying to compute, will be a very good opening game in your understanding the theory of predictability. Thank you.